सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
So, in the previous lecture you would have got some idea about what that so-called basic activity or what we are calling as RTL, that is register transfer level activity. Good. And I also with reference to instruction fetch, I was giving you some idea about how the CPU memory interact, and from that we saw what exactly we mean by the register transfer level. Now maybe I will try to review that from the hardware point of view. I was just telling you conceptually what it was. Now we will just take a look at the same thing slightly from a different perspective. Now here is the bus which connects the CPU and memory, and then we have the CPU and memory sitting on the bus. Now actually we have to go into some details of the CPU and memory here, right? Okay, right, that's the CPU, let's say, and then the memory. Let's not really bother about how many lines and in which direction, etc. We have a set of lines. Now I will go into the details of these. Now what did we say? In the first state, shall we also work out what's actually happening? That is, at the state level we said the state is defined by the clock period, right? Now this is, each one of these clock period is the one forming the state. If you recall, we are talking about 4 states, okay, in the instruction fetch, that is constituting the machine cycle. That's what we were seeing yesterday. We'll work it out again. Now that whole thing is the machine cycle, and we took the example of instruction fetch. Fine. It can be any other thing also, and the machine cycles, the next machine cycle continues after that. Good. We said the CPU places the address. Now I am going into the details of this set of lines. Okay. Now the CPU places the address, and so we have just call some register. We said earlier that the CPU will have some registers, different types of registers. Now I'll just call this particular one from where the address comes as the address register. So CPU places the address register on the bus, some set of bits, okay, some code. It places the address on the bus. Fine. And what about the organization here? Said that this consists of different locations. So this address will be received by some part of the circuit which will decode that particular address, okay, decode that particular address, which will help select one of these. Let us say for the address that is placed here, this is the specific location that has been identified. So the contents of that location in our case will become the data. Now what exactly is the data here? Because we said it's instruction fetch, this data is nothing but the instruction. Okay, fine. That's what it is. So this particular one is an instruction. The CPU is trying to fetch that from the memory. So it places the address. This is what we said. That is, we call this particular one as say T1, the next period as T2, then the next as T3, and the next as T4. Now let us write down. During T1, we said the CPU places the address on the bus. And also we saw subsequently a read control is placed on the bus and memory will place data on the bus. Obviously, when we say bus, these are different parts of the bus. Now, we may just say that T1, during T1, the CPU places the address on the bus. So I will just call that part of the bus as address part of the bus. Okay, I'm just qualifying this. So that part of the bus on which the CPU places the address. So this is actually the activity of CPU. CPU has placed address on the address part of the bus, and we also saw the previous lecture that is during T2 it is generating, that is the CPU is generating a control signal. Okay, we just called it as a read control signal. Alright, so I will say read just to indicate that it is from the controller. I will use like this, and then the read control signal is placed on, let's say, the control, how does it matter? I'll use some other thing, control part of the bus. This also is done by the CPU. Actually, the CPU indicates that it wants to read something from the memory. Now, being an instruction fetch, we know that it wants to fetch the instruction into itself, that is from the memory into itself. Good. So let us say that there is a controller. Okay, where shall I specify that? Now I may need some space, so I'll just say, okay, here is some control part. Okay, the control part of the CPU, and the CPU places, in this specific case, it places this signal read. Actually, here address has come, that's what it is, right? So we'll try to. Good. The CPU has placed the address. CPU has indicated that it wants read to be done, right? Now, receiving this signal must trigger the memory to respond, right? And the moment the address is placed, we can just take that address has been decoded, that is, this is the address part, this address has been decoded, and in the entire memory organization one specific location has been identified, that's because of the unique address. Okay, and then when the read signal comes, alright, when the read signal comes, say I will just assume that this read signal goes to some control part of the memory. I don't know what exactly it is, some control part of the memory, that is the read signal goes to some control part of the memory which enables that this being placed on the bus. Okay, that is how it must be. So this particular one, the contents of this must go on to the bus. Now what exactly it is? It is actually in our case instruction, because this is a machine cycle referring to the instruction, but it just in general we will call this as the data. So that's what we say by saying that during T3, right, the memory responds by placing the data, what exactly is this data? In our case it happens to be data, whatever it is, the contents. Okay, in our case it happens to be instruction. If you want, I'll just identify that as instruction, and this is the content of memory. Now this has gone on to the bus, that's what we said the previous class. Actually the part of the bus is the data part of the bus. Okay, so now you can see, though different things come on the bus, now we are getting a clear picture that the different things can be identified by placing them on different parts of the bus. Fine, good. Then if you remember, we said during T4 the data that is available on the bus, okay, that is the data that is available on the bus will be read by the CPU into a register, and this being instruction, we also said that this goes into instruction register. Okay, an instruction register that let's identify as some register, that is the instruction register. So the data that is coming over the bus is routed to this particular one. This in fact is the data. Okay, the data that is routed into the instruction register. Good. Now is it clear what we mean by register transfer level? So from this register we are putting onto a set of signal lines. Now that is one transfer that takes place in T1. Then from this part of the CPU, the circuit, control circuit, a signal, just an 1-bit signal, okay, that goes, that is a read signal that goes to the bus. That's another transfer that takes place during T2. Then in T3 we are assuming, there is an assumption that is made right here, we will talk about it a little later, okay. We are assuming that the memory is ready to respond because it knows from where to get the information, that is the data in this case being instruction, and it also knows what it should do. Now this being read, obviously this means the CPU wants to read from the memory. So this is placed in the next state T3 onto the bus. Then again it's assumed that CPU knows by the period T4 starts, okay, by the period T4 starts that the data is available, and then the data is transferred again, transferred again to I register. Now on the other hand, if it were not an instruction fetch, but it is a, say, an operand fetch or a data fetch, suppose if it were an operand fetch, which normally also we call data, right? This is why I told right in a few lectures before, when we use the term data, be careful. It's a very general term. Operand also will be referred to as data. The contents of any memory location will also be referred to as data. Correct. Now instead of instruction fetch, if an operand fetch comes, obviously the contents of that location will not be routed to instruction register, but it will go to another register, call it as, say, D register for some data register, okay, that's what we mean. So some other register. So this is how we have the architecture of the CPU also evolving. Okay, we'll come back to this a little later. Now these are the basic activities, and most of these take place during one clock. Suppose the clock period is 1 megahertz, what we are saying is within 1 microsecond this transfer takes place. If it were 10 megahertz, then within 100 nanoseconds this is taking place, and so on and so forth. Good. So let us try to learn a few things here. What is it? one thing that we noticed is the bus we started saying as a set of signal lines for communication or interaction between two things on the bus, specifically in our case CPU and the memory. Now we are seeing specifically that there are different things that come on the bus. So in one case address comes, in another case a control signal comes, in another case the contents of a location which we generally call as data that comes. So obviously the bus consists of different parts, and specifically we can even generalize from this that there is an address part of the bus, there is a control part of the bus, there is a data part of the bus. Okay, now we have some idea about the bus also. That is, a bus essentially will consist of address, then data, then also the control part. Okay, good. Now you remember I was talking about an 8-bit CPU or a 16-bit CPU and the memory which is organized. Now an 8-bit CPU means it is capable of dealing with an 8-bit data. So in that case it is meaningful to have the data part of the bus 8-bit wide. It's meaningful, okay, but it's not strictly necessary. For instance, if it were a 16-bit CPU and the data part of the bus happens to be 8-bit, it only means that in 2 steps the 8-bit data will have to come from the memory and the CPU will start processing after it gets those 2 bytes. Okay, fine, that's what it is. So you would find for instance, if you take a microprocessor, let us say, we will talk about an 8-bit microprocessor, and that means essentially it's an 8-bit data and the address may be a 16-bit address and control signals depending on the complexities of the processor. So for supporting a processor which handles 8-bit data, 16-bit address, here also we would expect an 8-bit part of the data bus, 16-bit part of the address bus and the control signals needed for the processor memory interaction. Well, more about bus we will see later. Now let's come back to this state activity, that is the lowest level activity. I said we had made some assumption here. What is that? We have assumed that as soon as the CPU demands that it wants to read something from the memory given this address, the memory is ready with the data, right? The CPU is addressing and then CPU indicates that it wants a read to be performed. We are assuming that as soon as the read comes, okay, the data will be made available by the memory and then will be placed on the bus. Well, where is the guarantee? The processor may be too fast, the memory may be too slow. For instance, if this period, okay, corresponds to let us say 100 nanoseconds, and if the memory is not that fast, it takes more time. Suppose from the time it gets the address and the control signal, in this case read signal, suppose the memory takes 200 nanoseconds, that particular thing is called a memory access time. Okay, the memory access time, if it were 200 nanoseconds, what is this memory access time? The time taken by memory to access the data and put it on the bus. Now we said the CPU clock, that is the CPU state clock period, that is corresponding to the state duration, each one, suppose it is 100 nanoseconds. Now what is it? From the time the address comes, yes, the memory has 200 nanoseconds, but from the time the read comes, that is during T2, the memory has only 100 nanoseconds. We have not said here precisely the access time means what. If you assume access time means after the memory gets all the information that it needs to prepare the data, which means you are talking about after T2. Now we find that after T2 we have only just 100 nanoseconds. That is, during T2 it generates the read signal, and then you have only 100 nanoseconds, and that is not sufficient for the memory which is slow memory. Right? Now what will it do? We are not bothered about it. We have immediately assumed and then said as soon as CPU wants, memory will respond. Agreed? Now in this particular case it is not really so. The CPU, the memory needs more time than the CPU. That is, basically here we have a faster CPU and a slower memory. So this situation can very much arise. What can be done? So obviously in the next state T3, the memory cannot be ready. That's what it means. So we have to introduce what is known as an extra state called a wait state. That is, in other words, we will have T1, then we will have T2, and then we have to see that the memory will have to indicate to the processor that it is not fast enough. In which case the CPU, you see, CPU is the master of the bus, right? It is the CPU which has to take a decision, but it must have enough input. We don't know what's here, whether it's a fast memory or a slow memory. Okay. Now assuming that the CPU, the memory can indicate that it is not fast enough, okay, then this particular signal, this will be coming from the control part actually, okay. This particular one again it will go to the control part of this. We'll have to go, well, how does it, okay, I will write here, okay. This will have to go to it. Now this particular signal basically indicates that the memory is trying to tell the CPU, well, you have asked me to do something, but I am not yet ready. Okay. So really this particular thing is called a ready input. Okay. Now ready input from the CPU point of view. Okay. So the memory generates a ready signal. Really what it does is, ready it will make 0, which means it is not ready. When it makes 1, that means it is ready. That is what it is, right. So as soon as the memory gets address and read, that is after T2. Now the memory will generate the not ready signal, which will be sensed, and on sensing that particular one, the CPU will introduce, let us say in our case, one more state. If it introduces enough. So we will just call this particular one as TW or wait state. Basically it means it is not ready. Okay, good. So and then in this case it is enough. One more state, it is enough, and then we can continue. Okay. Then essentially what we have here is the T3 part, but it is not the same as T3, it is extended, right. So I will just call it as T3 prime. It is different from this because the wait state has come in actually, okay, and so on. Agreed? Now where exactly this particular information will be included in our design? Now let us go back to that chart I started with, that I introduced in the last lecture. I was talking about computer or CPU as a state machine, right? As a state machine I was introducing, right? That's how we started looking at what the state is. Good. and then I was showing a state box, recall. Now let us try to draw the chart for this right now. Incidentally, I think I did not mention that particular chart is not very much different from flow chart, because it basically tells the flow of activities, right? But it's slightly different from flow chart in the sense, in the flow chart generally we do not introduce the signals with some names. So here we will introduce the output signals and the input signals with names. Okay, so this actually is called a state machine chart, and because the particular chart will be describing the flow of activities, in other words algorithm, right? This one is called an algorithmic state machine chart. Okay, algorithmic state machine chart, that is what it is. Okay, or just an ASM chart, that's what it is. So let us try to develop this ASM chart which I was introducing in the previous lecture. Now yeah, why not we call, just we have to name the state. I will just name the state as T1, okay, which corresponds to our this first state T1. Okay, in state T1 a control signal address must be placed on the bus, that's what it is, right? So I will just say address is placed on the address part of the bus, so that I will leave, I will just indicate for want of space. Okay, that's what it is, this address is placed on the bus, that's what's taking place in T1. Fine. Next it goes to the next state, which we know is the state T2. I'll just name this next state as T2, in which case read control signal goes onto the bus. So this in fact is the, you remember in the state, this is called the state box. In the state box we indicate the signal, that is, you remember I was saying output. Okay, why do we call this as output? Essentially you can see here the controller in the CPU must generate an output, so that that output, okay, will make this address register place it on the bus. So we achieve the purpose, right? Actually when we say output, what we are talking about is the controller's output. Okay, so the ASM chart which we are drawing, we are just going to draw for this particular one, which says for one instruction fetch. Essentially what you see here is the end result. At the end of this state T1, address will be placed on the bus, and that is caused by the controller's output enabling the address register go on to the bus. Get it? That's what it is. Good. So address going to the bus is the end result. So the controller must generate the signal which causes that. Okay, we'll come back to that a little later if necessary. Then the same thing, the controller must generate the read signal and put it on the bus. That must take place in the next state T2. Now instead of this, we will assume this is the situation, in which case what is to be done is we have to check whether the state of this input, now this is the input which again goes to the controller, right, must go to the controller really. What is the state of this ready input? Ready input of course goes to CPU, which means essentially it goes to the controller of the CPU. What is the state of this ready input? Is it ready or not? What is memory ready or not? That is what it is. So if the memory is not ready, that is 0, then just stay in the same state, meaning the read control signal which may have been generated, extend it further, that is it is not ready, so go on, that is what it is. So stay in that. On the other hand, if ready is 1, meaning the memory indicates that it is ready, then we can go to the next state T3, in which this taking place. There is a memory, data is placed on the bus. So I will just put it as D. This is in fact for causing this. Data goes to the bus. Actually, the controller is not concerned with that. The controller will only see to it that it keeps waiting, it will not go to the next one. So this is purely a memory activity. CPU is only waiting for that, and then once the processor goes to state T3, the next is T4. Okay. Good. So which means after this, the data that is available on the bus goes to instruction register. So say that is the data which is available on the bus. Okay, that's why same thing, instead of saying the same thing, whatever data that is available on the bus goes to the instruction register, and so on, it proceeds. Now this in fact is the ASM chart which describes the activities which in some way I have indicated here. This is for instruction fetch. Good. Now you can see here that the CPU controller must generate the signal, as I already mentioned. The controller must generate the signal so that the address may be placed on the bus, and in T2 the controller must generate the signal so that the read control signal will go on the bus, and then after T2 we are seeing that the controller is looking for the input, right, that in fact that input is from the memory. So who knows that the CPU memory needs more time or it can respond at the same speed as CPU? The designer obviously, he chooses, right? He knows that the CPU clock is 100 nanoseconds and memory needs 200 nanoseconds. Whenever the CPU demands, okay, whenever the CPU demands, memory is going to respond after a delay of 200 nanoseconds. So the designer knows. Instead, if he had chosen a memory with 50 nanoseconds access time, absolutely no problem, right? The more, even during part of T2 itself, the data would have been available. That's what it means. So the designer chooses the CPU and the memory, and so it is the designer who will have to see that the controller which is associated with the memory generates this ready signal or not ready signal appropriately. Okay, some logic, that is address and read, when it comes, ready or not ready must be generated. So that is the logic which will be included in this. So on sensing the ready, the CPU controller decides whether it can go to the next state or whether it should continue in the same state, right? Now, if you want this particular thing can be slightly rewritten, this part of it, okay. If you don't, if for instance this particular thing should not be generated, okay, in case you need it, then this can be slightly modified and we can introduce a so called wait state like this. When it is 0, then it goes into a state called wait state TW, let us say by name TW, and in which case it does nothing, see, it just waits and then it keeps checking whether the ready is 0 or 1, okay. If the ready is 0, it continues to be in the same wait state. When it is 1, it comes to this point, okay, this point it will come to. It all depends. Can either have it that way or this way. Well, both are permissible. It all depends on how exactly this read will be available, okay, to the CPU bus or whatever it is. Good. I hope now you got some idea about what a state machine is. State machine is one which goes through sequence of states, and in each state it generates an output, and whenever necessary it also looks for an appropriate input, and then it decides what must be the next state. Now, for the present state T1, surely the next state is T2, whereas for present state T2, the next state can be TW or T3. It depends on the state of the input. Now, I have just done for one machine cycle. So, like this it must be done for all the machine cycles, right, and then depending on whether the what comes over from the memory is instruction or part of an instruction or operand, okay, that is during data fetch or operand fetch, then appropriately that particular thing will be routed to different parts of the processor, right. So, you can see now when we talk about this, essentially we are talking about the sequence in which the various control signals for CPU must be generated, except in this particular case we note that though we have marked here, it is not the CPU controller which generates, does it, the memory response, okay. So, in fact from CPU point of view you can even remove that, that is what it means, because this particular ASM machine like this we have to go on doing for all the this thing machine cycles, which means what is it machine cycle? A machine cycle is part of an instruction cycle, right, is it not? So, we are talking about instruction cycle that consisting of different machine cycles, and we have just taken an example of one machine cycle. Now, we have to do for all instruction cycle, which means we have to take for all the instructions, all the instructions supported by the CPU or all the instructions of the CPU, and then work out this low level activity, that is the register transfer level activity. So, that when the sequence is ensured, then we say that the controller goes through those steps, and depending on the nature of the input and the state, it will generate the appropriate output and the next state, fine. So, the starting point of a CPU design is the instruction set. That is the first step. The starting point of design of instruction is, design of CPU is the instruction set, and depending on the application the set of instructions will vary. Okay, so start with the instruction, and for each instruction work out what are the machine cycles, and then for each machine cycle find out what are the RTL level activities, and that describes the behavior of the machine, in this case the CPU. That's why we say the ASM chart describes the algorithm. And what exactly are you getting at here? You are getting to know the behavior of the controller of the CPU, which will ensure the various activities as given in that. Okay, so the ASM chart for the system, when we say, let us say CPU, when we start, actually we are talking about the ASM of the controller, algorithmic state machine, and then we develop the state by state behavior of the controller, and that controller will generate the necessary signals for these various operations. Now that brings us back to two things. What did I say earlier? I said the CPU essentially consists, CPU design essentially consists of data path and the data path control. Okay, data path control. So now I have been talking about this control. Now what is the data path? Okay, now what is the data path? The data path essentially is the path over which the data should move. What is the data in this case? In this case, the data that it handles is the address. The data that instruction register handles is actually instruction. So that data path, and then see, from the bus point of view, the data comes over the data part of the bus. If it is instruction, it gets routed to instruction register. If it is data, it must get routed to the appropriate data register. So now to get at some idea, we have to go into the details of these. What are the various registers that we have and how they are internally organized? In other words, we have to go into the architecture of the CPU to further understand what is going on. Okay, the further aspect of the design will depend on how exactly you organize the set of registers. So there will be some registers which handle only address, some registers which will handle only data, and some registers which handle instruction, and some other registers for some other purposes, say included for controller, and so on and so forth. So the next thing is, having got some idea about what is the control sequence, okay, we have to go into the architecture of the CPU. Now before we go into that, I will mention one important point here. Well, what's the important point? Let's not forget that the computer ultimately executes a program which consists of instructions, and the instruction is executed during an instruction cycle which consists of machine cycles, and then we went into the details of the machine cycle, that is the states. Now the program is executed one instruction after another instruction, which means from the CPU point of view, okay, from one address to the next address and so on so forth. This is the normal sequence. So actually this particular address register, though just called in general as address register, may come from one counter. For instance, the counter initially may point to this, and the next part of instruction or next instruction may come from the next one, which means this plus 1 and so on and so forth. Specifically the address register which gives the instruction address is called a program counter. Okay, of course, the particular sequence may be changed subsequently. That is so. Similarly, there may be other instructions which make use of some other address registers. So this is very common, and then through the address register, actually the source for this address register will be program counter or some other, say, memory address register and so on and so forth. And this side we have just a path that is set up for the address. Incidentally, these various signals, they all form part of this bunch. Okay, we have only blown up and then worked out the details. Now, another thing is again related to the program and the sequence of instruction execution. Right? That is, when it comes to the last point, that is the state, it's a small step. One register transfer level activity is that's going on. In other words, the program consists of sequence of instructions, and ultimately when one instruction is taken, essentially we have a sequence of these steps. These are actually called micro instructions because we are talking about an instruction consisting of a sequence of micro instructions. Right? Now, if a particular programmer can develop a program at this level, then he is really called a micro programmer. Now, there is a difficulty here. If one can develop the micro program, what happens? The whole character or behavior of the CPU is altered. Agreed? So really we are talking about a fine grain level programming, whereas usually the application program is written at a very high level. He will not bother about all these lower level transfers. But if the programmer has given the capability to write the program at that low level micro program, so he is really altering the very basic character of the controller, which means he is altering the basic character of the CPU itself. Well, there are some micro programmable processors also, but remember that that is not true of any general purpose processor. Now, this control unit can be designed making use of the hardware which implements these micro steps, or we can have a micro program which indicates these, and then we can have a controller based on that. Okay, if the controller can be designed using hardware circuits, or you can have a micro program which again in turn indicates these micro steps. Agreed? In which case this becomes a micro programmed controller. At that level, from the general purpose processor user point of view, he will not be able to alter. Otherwise, if he can, he is going to alter the character of the CPU itself. Good. So we will talk about this micro program controller and the micro program itself in subsequent lectures. But before that, I would tell you one thing, that is, I said the controller can be rigged up or developed using hardware circuit, and if we use micro program control, that particular thing will be called a firmware design. What is that? Basically, I said either the sequence of the control signals, right, that can be realized making use of hardware circuitry. On the other hand, if we use micro programs, then by changing the micro program you can change the character, and so as long as you don't change, it is firm enough, right? So a firmware design would be essentially meaning a micro programmed controller implementation. Fine? Well, that's it for the present. In the next lecture we will take a look at the data path architecture, because having talked about data path control and how it comes about, it's time we take a look at the architecture for a typical data path, something we will assume and proceed with.